Good evening everyone. Can you all hear me? Excuse me, am I audible?
Yes, ma'am.
Okay, thank you. So I think let us start today's session. Before starting, let me introduce myself. I am Harsha from IIT Tirupati. This is a session for the problem solving for the Introduction to Abstract and Linear Algebra course provided by the NPTEL. And we will solve some problems related to the week 3 lectures. So I hope you have already seen the videos of the week 3. So we will solve the problem. So let us go to the session. Is the screen visible for you? Is my screen visible?
Yes, ma'am.
Yeah, okay. So let's begin with the first question. So here the question is the number of fold singleton generators of the cyclic group Z plus. So we are given a group Z plus. Z plus is the group. So the question is to find the generators of the cyclic group, that is elements A in Z such that generator A equal to set of fold NA such that N belongs to Z. This is the group generated by A and A is the generator. So we want to find the generators. That means this generator A group, this group should be equal to Z. So we want to find the set of fold A such that this condition 1 is satisfied. Okay, first of all, can anyone say one generator of the group Z plus? One symbol. What can be the generator of Z so that it should satisfy this condition? We will see. Let us take A equal to 1. So what will be the generator of A? That is generator 1, which is equal to set of fold N into 1 such that N is an element of Z. This is same as set of fold N such that n belongs to Z. What is this set? Set of all n such that n in Z means, what is this? Excuse me, can anyone answer this?
Set of integers.
Yeah, this is set of integers. This is set of integers. Set of all elements in Z means set of all integers. So what we are getting is the subgroup generated by 1 is same as Z. So 1 is a generator of Z. Okay, is this clear? Is this clear? This one is a generator of Z. Okay, now let us go to other elements. See, if I am taking A equal to 2, what will be generator A? That is, what are all the elements generated by 2? By definition, what will be the set? This is the definition, set of all n such that n in Z. So here A is 2. So what will be here? Yeah, 2n. Set of all 2n such that n in Z. So here what we will get is all multiples of 2. Here we will get -4, -2, 0, 2, 4, etc. This is the set of all 2n n in Z. So can we say 2 is a generator of Z? Is 2 generates Z?
Yes.
Yes, why?
To generate 2.
See, an element A generates Z means if we are writing set of all NA, then this set should be equal to Z. Here we are finding the generator 2. So what we are obtaining is this. Is this set equal to Z or not?
No.
No, this is no. Yeah, like if we are taking all the means all the multiplication means 2, here it is addition operation, so 2, 2 plus 2 and so everything we are taking. So if it becomes Z means the original group, then we can say 2 is a generator of Z. Here 2 does not generate Z. Okay, so 1 generates Z, right? In the same way, can you think about any element that generates Z? No?
No.
Okay, let me take one more example. If I am taking 3, again if I am taking 3, what we will get is in the same way, we will get set of all 3n such that n in Z. Again it is not equal to Z, right? That means if I am taking any element m strictly greater than 1, it will be a multiple of generator m means multiple of m. So this generator m cannot be Z, right? Now we examined all the cases of positive integers. Now what about the negative integers? Can any negative integer can be a generator of this Z? Not that 1 is a generator of Z. In the same way you can think in the negative also. Okay, let me go to -1. What about -1, generator of -1? Can anyone say by definition what will be generator -1? See, this is the definition. Generator A means set of all NA, N in Z. So what will be generator minus 1?
Minus 1 into n by
Yeah.
z, n belongs to z.
Okay, this will be minus 1 into n such that n in Z. What is this? Set of all minus n such that n in Z. So, now what is the conclusion? Whether minus 1 generates Z or not?
Yes, ma'am.
Yes, because n in
Yes.
Z minus n in Z means like corresponding to each n we have minus n means we will get all Z, right? This is same as Z. That means minus 1 generates Z. So, what about minus 2? What will be generator minus 2?
No, it will not.
No, because it is all minus 2n such that n in Z. Again, it is same as the set of all multiples of 2. So, this is also not equal to Z. So, if we are taking any other integer 1 and minus 1, we will not get, that is, that integer will not generate Z. And as a trivial example, let us consider 0 also. So, we examined all positive integers and negative integers. So, what is generator of 0?
0 into n belongs to z.
Yeah, only 0, because 0 into n such that n in Z is the, by definition, this is same as 0. So, of course, 0 does not, because it is trivial element, always trivial element will not generate the set Z, group Z. Okay. So, the generators of Z are only 1 and minus 1. Okay. So, we got two generators. What are all the two generators? 1 and minus 1. Here the question is number of generators of the group Z plus. So, it is 2. Is that answer clear for everyone? Yeah, if anyone is having doubt, please ask. Basically, this session is for an interaction with you because it will be easy for you to solve the other problems. So, I hope you will respond to my questions. Okay, now we will go to the next problem. So, here we have given one group set 2027 with addition. Addition means here addition modulo 2027. So, this is the group. So, the question is the distinct subgroup of the cyclic group. So, basically for a group, we can ensure two subgroups are there. What are all the two subgroups for a group? For any group, we will have two subgroups. For any group G, we have two subgroups. What are all that?
0 and vector.
Can you speak a bit louder?
Zero in itself.
Yeah. Identity means the trivial subgroup and G itself. G itself is a subgroup of G and identity is also a subgroup. So, in the same way, here we have identity 0 means in G means here it is the identity element E. In set 2027, 0 is the trivial element. So, 0 itself is a subgroup and G itself is a subgroup of set 2027. So, we need to find whether there exists another subgroup other than these two. Suppose, okay, what do you think whether it will have a subgroup or not other than these two? Any guess? Okay, we will take a subgroup H which is not equal to set 0. That is not a trivial subgroup. what is that it is not a trivial subgroup means? Can we find any element other than 0 in H?
Yes.
Yes. Okay. Let M is an element. M, of course, it will be not equal to 0, which is an element in H. See, I am taking M because M is an integer also, because M in H means M is an element of set 2027. So, M is an element of H. Okay. Now, what will be the order of M? Order of M means the order of the subgroup generated by M. Right? Okay, let us see. Yeah, let us see what is the subgroup generated by M. What will be the subgroup generated by M?
M and such that N belongs to Z.
Yeah, M n such that N in Z. Actually, this is under modulo 2027. So, we can write, first we will take M when n equal to 1. When n equal to 2, we will get 2m, then 3m, etc. etc. Okay. So, this will be the generator M. Finally, it will reach at some nm. This will be finally some nm. This nm will be equal to the identity 0. Okay. What is the identity? Identity 0 is same as 2027 because we are taking the addition modulo 2027. That means the remainder when divided by 2027. So, 2027, when we divide 2027 by 2027, we get 0. So, we need nm equal to 2027. See, this 2027 is a prime. So, what are all the possible divisors of 2027?
1 and x.
1 and 2027. Here we get nm equal to 2027, right? So, m is a positive integer, therefore n should be equal to 2027, n equal to 2027, because otherwise we cannot write 2027 as the product of n and m, right? Is that clear?
No, ma'am. I'm not getting this. This.
Okay. We'll see once again. First we want to, okay, is this clear? 0 and G are subgroup of, sorry, 0 and 2027 are subgroup of this. Is this clear?
Yes.
Yeah. Okay. I think we will approach in another way. Okay. So in the class, you have talked about, I think, if A is an element of a group G and order of A equals n, then order of A power m equal to n by GCD of mn. This you have seen already, right? In the class?
Yes, yes.
Yes. Okay. Now we will go by this approach. This is for a general group. Now here we have instead of G we have set 2027. Suppose H is a non-trivial subgroup. Suppose H is a non-trivial subgroup of G. that implies there existed an m not equal to 0 in H, right? Is this clear?
Yes.
Okay. Here instead of A, we are taking the element 1 in G. Okay. What is the order of 1? Here G is what is the order of 1?
10. 1 into A.
This
2027.
yeah, 2027.
Yes.
2027, because 1 is written as first 1, then we will add 1 with 1 plus 1, 2, then 3, etc. we will go. When we reach 2027, instead of 2027, we can write 0 because this is addition modulo 2027. So, order of 1 is 2027. So, instead of A, we are taking 1 and order of A is n. So, this is our n. Now, here we have written order of A power m in the multiplicative sense. So, here we are, our operation is addition. So, instead of order of A power m, we can write order of mn. Right? Is this okay? Because we are like adding m times A. Is this clear?
Yes.
Okay. What is the A here? A we have taken as 1, which is equal to order of m. Right? So, by this theorem, we have order of A power m is n by GCD of mn. Here n is 2027 and GCD of mn. GCD of m 2027. We don't know what m is. M can be any number, where m is any number between 2026, because m is not 0 we have taken, but m can take any value from 1 to 2026. Okay. So, what will be GCD of m 2027? Because 2027 is a prime. So, what will be this value?
1.
1. Because 2027 is having only 1 and 2027 as factor. So, this GCD is 1. So, what will be order of m? 2027 by 1, which is equal to 2027. Is that okay? Is this clear for you? Any doubt? If you have any doubt, you can ask. Okay. So, here we got order of m is 2027. What we have taken is m is an element which varies between 0 and 2026. For any m in 2026, we get order of m equals 2027. That means in set 2027, we have elements 0, 1, 2, etc. up to 2026. If we are taking any of these elements, we are, what is that this order of m means? Order of m equal to cardinality of generator of m, right? What is cardinality of m? What is generator m? M, 2m, 3m, etc. So, here m, 2m, 3m, all these elements are distinct, right? Okay, are you able to follow?
Yes.
see, what I am writing is generator M. Generator M means M, 2M, 3M, etc. up to 2027 M. So up to this it will go. After that again it will repeat. Means again I am taking 2028 M means it will go to M. So the maximum possible value is up to 2027 M. And this is the order of A 2027. So up to this we have 2027 elements, 1 to etc. 2027 elements, and all these elements will be distinct because we already have a theorem such that if order of A is n, A square etc. A power n are all distinct. This is also you have seen in the class, I think, right? Do you know about this theorem? Okay, so if order of A is n, A square etc. A power n are all distinct. Here we already got order of M is 2027. So here M, 2M etc. 2027 M are all distinct element. Okay, so here we got 2027 elements. We started with M is in the subgroup H. If M is in group, what about 2M? 2M belongs to H or not?
H is a subgroup, then naturally 2M is a member in H.
2M belongs to H, right? In the same way, all these elements up to 2027 M belongs to H. Is this clear? Okay. So all the 2027 elements belongs to H, and all these elements are distinct by this theorem. So what we can conclude, and H is a subgroup, means H is a subset of our 2027 with the H having 2027 element. What this implies? Is this H and 2027 are equal? Is this clear from these two conditions? H is a subset of set or subgroup of set 2027, and H is having the same number of elements of set 2027. So the only possibility is they should be equal, right? Yeah. So H is 2027. So what we started is H is any non-trivial subgroup. So such that there exists a non-trivial element, that is there exists a non-zero element in H. So if there exists a non-zero element in H, all the elements, that is if M is in H, 2M up to 2027 M are in H. That means H finally becomes the set 2027. Okay. So what will be the conclusion? Is there any non-trivial subgroup for set 2027 other than the set 2027?
No.
No, because if we are starting with such a non-trivial subgroup, we are finally ending that this non-trivial subgroup is same as the set 2027. So we have only two distinct subgroups.
Excuse me, ma'am.
Yeah, yes.
Am I audible?
Yes, you can tell.
Actually, the question is number of distinct subgroups, right now?
Yes.
Since 2027 is prime, the only subgroups are one and the group itself.
Yeah, only subgroups are trivial group and this group itself.
Using Lagrange's theorem, we will reach the result right now.
Yeah, see, yes, that is the very easy method using Lagrange's theorem. The cardinality of subgroup divides the cardinality of group, right? But as of now, I think you have not covered the Lagrange's theorem, right?
Right, ma'am. But comparing that, this is tedious process, right, ma'am?
Yeah, this is the easy concept. Like we know that the cardinality of subgroup. Okay, I will tell that also then. Lagrange's theorem. If order of G is finite, G is a group, G star is a group, and order of G is finite, and H is a subgroup of G, then order of H divides order of G. So here order of G is order of Z 2027, which is 2027. Since 2027 is prime, we have 1 divides 2027 and 2027 divides 2027. These are the only possibility. So corresponding to this only we can have the subgroup. That is, corresponding to this we will get the trivial subgroup, and corresponding to this that Z 2027 is our possible subgroup. So these are only possible subgroups. But as of now, I think you have not covered the Lagrange's theorem. So before going to Lagrange's theorem, you have to see all the left coset, right cosets, and you need the proof of the Lagrange's theorem also. So that is why I am using this a bit it is a bit complicated, but it's okay. Like you can use the Lagrange's theorem also. You just need to find the answer only. So you can use it also. But before studying the Lagrange's theorem, like we can explain this problem like this also. Is this okay?
Okay, ma'am.
Yeah, if you feel any difficulty, you can just use the Lagrange's theorem. Anyhow, you will learn the Lagrange's theorem in the next week. Okay, if anyone is having doubt, you can ask in this solution. Okay, so let us move to the next problem. So here we have given a group Z star where star is defined like this. If A and B are elements of the group Z, elements of Z, then A star B is A plus B plus 1. Okay, so the question is to find the inverse of A. Okay, let B be an inverse. Okay, inverse is unique, so B be the inverse of A. So what will be this? A star B equal to B star A equal to identity, right? Okay, now what will be the identity element? What is E here?
-1.
-1. Okay, if E is -1, we will check A star -1. What will be A star -1? A plus -1 plus 1, which is equal to A. And what is -1 star A? Excuse me, 1 minute.
-1 plus A plus 1. -1 plus A plus 1.
Yeah, sorry, can you repeat?
-1 plus A plus 1.
Okay. -1 plus
Plus
A
A
plus
plus
1. Okay, this is A. Okay, so -1 is the inverse, right?
Identity element.
Oh, sorry, identity element. Okay, now let us see what will be the inverse. A star B should be equal to what? -1. What is A star B? If B is the inverse, A star B should be equal to -1. A star B by definition A plus B plus 1,
Plus 1.
which is equal to -1. That implies B equal to -A minus 2, right? Okay, In the same way, A star B should be equal to minus 1 and B star A should be equal to minus 1, right? Here also what we will get is B plus A plus 1 equals minus 1. That implies B equal to minus A minus 2. So in the both sense we are getting B equal to minus A minus 2. So option D is the right answer. Is this clear?
Excuse me, ma'am.
Excuse me, ma'am.
Yeah, yes.
We take the identity as minus 1.
Can you repeat?
How did you take the identity as minus 1?
Okay, we will see how we are getting the identity as minus 1. So, by definition, A star B equal to A plus B plus 1. Let E be the identity. We don't know what is identity. We are going to find the identity. So, we need A star E equal to E star A equals A, right? Is this okay?
Yes.
Yeah. What is A star E? A plus E plus 1. What is E star A? E plus A plus 1. This should be, both should be equal to 1. So we will start with this equation. A plus E plus 1 equal to A. So we can cancel A. This is addition. Of course we can cancel both A, right? This is E plus 1 equal to 0. Then what is C?
That's one.
Minus 1, right? Same way we can solve this equation also. Again we will get E equal to minus 1. This is how we are getting identity. Actually someone told E is minus 1. That is how I started with the minus 1 here. First we need to find the identity and then we have to solve that A star B equal to E, and then what is B, where B is the inverse of A. Okay. Is that clear now? Okay, by the way, we have found for every element we found an inverse exists and an identity also exists. Even though they have given it as a group, we will check whether all the axioms of group satisfies. What are all the other axioms we need to check here? Because we already found the inverse and identity. So what are all the remaining things?
Closure and associative.
Yeah, closure and associative. Okay. What is A star B, which is equal to A plus B plus 1? This of course belongs to Z, right? So closure property is satisfied. Now we will check the associative also. What is A star B star C? How can we write this? What is A star B? A plus B plus 1. First we will apply A star B for the associativity, then star C. So what will be the answer here? Can anyone tell?
A plus B plus 1. A plus B plus C plus 1.
A plus B plus 1 plus
C plus 1.
plus C plus 1. Because if A and B are here, A plus B plus 1. Here A plus B plus 1 plus C plus 1. So A plus B plus C plus 2. In the same way we will solve the other way, A star B star C. First we need to find B star C. What is B star C? B plus C plus 1. So what will be here? A plus B plus C plus 1 plus 1. This is also A plus B plus C plus 2. Okay. So from this we get this is associative also, and identity and inverse are already proved. So we got Z star is a group also. Okay. Here you can see that here the set is Z, means the underlying set is Z, but the identity is not 0. Identity is minus 1. What that means is this identity and inverse are keeps on changing when the operation changes. If it is addition, we already got 0 is the identity. But when the operation changes this to the star, identity is -1. So identity does not depends on the set actually. It depends on the what operation is going to perform. Okay, is there any doubt in this question? So anyone is having doubt? Okay.
Where we
Yeah.
Here you have taken the star as the plus, no? Star as the plus in the plus sense.
Star is not the plus operator. Star is this operator, a plus b plus 1. What plus operator? Yeah, what plus operator means is if a, b in z, a plus b. This is our plus operator, right? Which belongs to z. Here the identity is 0. But here the operation star. Star is a plus b plus 1. This is the operation.
Okay.
Yeah. Did I answer your question? Any doubt? Extra? Okay. So we will move to the next problem. So here we have two statements. One is symmetry group Sn is non-abelian for all n greater than or equal to 1. Is this true? Anyone?
No, ma'am.
No. Okay. It can be abelian also. Right. For we will take first S1. What is S1? S1 is the set of, like if we are taking the set 1 only one element set, then set of all bijections in the set of all permutations in this set is S1, right? So we will get the only identity permutation here, only trivial permutation is here. Of course this S1 is abelian, right? Is this clear? S1 equal to 1 1, that is 1 is mapped to 1. This is the only possible element in S1. Of course it is a trivial group, abelian. Clear? So we can say symmetric group, here they are saying Sn is non-abelian for n greater than or equal to 1. For n equal to 1 it is abelian. Now we will see for S2. Okay, what are all the elements in S2? S2 means the permutations in set 1, 2, right? What are all the possible elements in S2?
Identity element and
Yeah, identity element.
the different combination. 1 goes to 2 and 2 goes to 2.
Yeah, 1 goes to 2 and 2 goes to 1. The cycle 1, 2, right? So any other possibility other than this?
No, ma'am.
No. Yeah, this is the only possibility. Of course, this is this abelian or not?
It is.
Yes, it is.
Yeah, it is also abelian. So what we got is S1, S2 are abelian. What about S3? I think S3 you have seen already in class. What about S3?
Non-abelian.
Non-abelian. S3 is non-abelian. So you know how S3 is written. You can just check with all elements whether it commutes or not. Of course, it is a non-abelian group. In fact, what we have a result is Sn is non-abelian for n greater than or equal to 3. Actually, for any n greater than or equal to 3 we are taking, Sn will be non-abelian, but S1 and S2 are always abelian. So we will just see how it comes. Sn is non-abelian for n greater than or equal to 3. Let us take whatever n. We can take 1, 2. 1, 2 is a cycle in Sn, right? 1, 2 and 2, 3. We are taking 2 elements in Sn. whatever the value n, it is having elements n greater than or equal to 3. So we are taking the 3 elements 1, 2 and 3. So we are having 2 elements in Sn, cycle 1, 2 and cycle 2, 3. So what will be 1, 2, 2, 3? 1, 2, 2, 3 means, okay, we don't know. Okay.
1, 2, 3.
1, 2, 3.
1 is 1, 3, 1, 2.
Yeah, actually the answer may change according to how we are taking the order. If we are considering the order first, we will get one answer. If we are taking this as first, then we will get another element. Actually in different text, they are using different way. Like in some text they are taking the composition first here and then first one. In some text the composition is first taking with 1, 2 and then 2, 3. So it is just depends on the text. You can take anything. Anyhow 1, 2, 2, 3, it will be 1, 2, 3, and in the converse if we are taking, it will be 1, 3, 2. Okay, here we are taking first 2 going to 3 and here 3 going to 3, that is 2 going to 3. Okay, here 1 going to 1, in this permutation 1 going to 1 and 1 going to 2, this is 1 going to 2. Okay, here 3 going to 2 and 2 going to 1, 3 going to 1. Here we are taken order first the second permutation and then the first one. In this way we have taken the order. So here we get 1, 2, 2, 3 is 1, 2, 3 and 2, 3, 1, 2 is 1, 3, 2. These are not equal. Okay. So any Sn, this is true for any Sn, Sn is non-abelian. So the only thing is in Sn we need at least 3 elements. So if less than or equal to 2, we have found it is abelian. Is this clear? Is this problem clear? Any doubt? Anyone is having doubt?
No.
Okay, we will move to the next problem. Yeah, here G is given as the set of all n by n matrices over Q. Then the question is whether G is abelian, non-abelian, finite or infinite. So what is G? Set of all n by n matrices over Q. Under addition, matrix addition means just the coordinate wise addition. So is G abelian? The operation is here addition, the usual addition. What do you think, is G abelian?
Yes, it is.
Yes, because if we are taking like some,
No, it is not abelian.
it is not abelian. Why?
It is a matrix multiplication, no?
No, under matrix addition. Operation is matrix addition.
It is under addition.
Yeah.
It is abelian.
Yes, it is abelian because it is usual addition. So coordinate wise, like if we are taking a plus b or b plus a, whatever, it will be same. So it is abelian. So is this finite group or infinite group?
Finite.
Finite. Is Q is finite or infinite?
Q is infinite.
Q is infinite, right? Q infinite. So we have elements of G as Aij, matrix Aij, where Aij are elements of Q, where I and J, 1 less than or equal to I, J less than or equal to N. Right? This is our matrix. Each entry belongs to Q. So what are all, like possibly can we have infinite number of matrices like this or finite number of matrices like this? For example, if I am taking one 2 by 2 matrices, this is Q1, Q2, Q3, Q4. So, how many possibility Q1 have, finite or infinite? Q1 can, how many possibilities, like, is it having a finite possibility or infinite possibility? Q1 is an element of Q.
It can be any number in Q.
Yeah, any number in Q can be Q1, right? So we have infinite possibility for Q1. In the same way, Q2 is also having infinite possibility. Similarly, Q3 and Q4. So corresponding to each element in Q, we will get a infinite number of matrices here, right? This is for a 2 by 2 example. So what about n by n? Like set of all this. This is infinite, right?
Yes.
Yeah, this is of course infinite because each Aij is what? Each Aij can be an infinite, like can have infinity possibility. So what we got is G is abelian and infinite. This is an infinite abelian group. Is this clear?
Yes, yes.
Yes.
Okay. Now we will go to this question. Z plus plus. We are given Z plus plus. Is this a group? Question is this a group or not? What do you think?
It's not a group.
It is not a group. Does it satisfy the associativity property?
Yes, yes.
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 Associativity is satisfied because it is the usual addition. So A plus B plus C will be A plus B plus C. And the closure property also satisfied, right? Any A plus B belongs to Z plus. If A and B are positive integers, A plus B will be a positive integer. Now, what about identity? Like, let A in Z. Is there any E such that A plus C equal to A?
No such E exists.
Yes, because if it is satisfied, the possibility is E equal to 0. And E equal to 0 does not belongs to Z plus. So Z plus cannot be a group under addition. So now I am just adding the 0 because we are lacking the identity element here. So I am just adding the union 0 also. Now under addition, is this a group or not?
Still it is not a group.
Yeah, still it is not a group because up to this associativity, closure property and identity property, this satisfy all these properties. But we have the inverse also. If I am taking any A in Z plus, any positive integer, the possible inverse is minus A, right? This does not belongs to Z plus. So it is not a group. Okay. Now the next question is set of all MNR. MNR means set of all n by n matrices under multiplication. So is this a group or not? Actually someone has already told that.
It is not a group.
Yeah, MNR under reason.
Under dot case, it is a group.
Is it a group? What can you tell once again?
Not a group.
Yeah, not a group. Because if I am taking like if I am taking some M2R, if it is 2 by 2 matrix or 0 0, is there any inverse for 0 0?
No.
Yeah, under multiplication, inverse of 0 0 does not exist.
Not exist.
So this is not a group. So the only problem is here actually the inverse. You can check all other, means matrix multiplication is associative and identity will be the identity matrix and associativity, closure property, everything will be satisfied. So the only problem is with the inverse. So we will consider GLN of R. Do you know what is GLN of R? This is the set of all. Yes.
Determinant value is 1. Is not equal to.
Set of all invertible matrices, right? That means this condition, we are taking this condition also together. So we are restricting to a particular subset of Mn of R where determinant is non-zero. So this will be a group. Is this clear? Is the problem clear for everyone?
Can I repeat the last one? GLNR.
Yeah, here the problem with the MNR is, the only problem is inverse does not exist for every element. So we are just considering all matrices which is having inverse. That is, we are considering the set of all invertible matrix. So the inverse condition is satisfied, identity matrix exists, associativity of matrices is satisfied, and the closure property is also satisfied, right? So this GLN of R under multiplication, will it be a group?
Yes, it
Yes,
is a group.
it's a group, yeah. So we are just taking a subset of Mn of R so that it is a group. Okay, is this okay now?
Excuse me.
Any doubt? Someone must.
Ma'am, how do you say that good GL of N comma R, generalized linear group system? What is there any special name for that?
Special name? What do you mean? I didn't get.
GL, it is abbreviation of something or?
Yeah, GLNR, I think generalized linear group, I think. I am not sure about that.
General linear group.
Yeah, yes. Okay.
Excuse me, ma'am.
Is this clear? Any doubt?
Hello.
Yeah, yes.
Ma'am, what can you say about SLN of R?
SLN of R means determinant is 1, right?
Right.
Okay, we will check that also. SLN of R means set of all n by n matrices with determinant 1. So what about the closure property? If two matrices determinant, like let me take two matrices A and B, A, B in SLNR. So what we want to prove is A dot B belongs to SLN of R, right? So in order to prove A dot B belongs to SLNR, what should be the condition? Determinant of A dot B should be equal to 1. This belongs to SLNR means determinant of A equals determinant of B equals 1. So what will be determinant of AB, which is equal to determinant of A into determinant of B, which is again 1, right? That means AB belongs to SLN of R. Is the closure property clear?
Yes.
Yeah. Now associativity actually holds because matrix multiplication is always associative. A into B C and AB into C are same. Now again, what will be the identity element here?
Identity matrix.
N by n identity matrix, right? That means determinant of I. What will be determinant of I, which is also 1? That means I belongs to SLN of R. Clear? And A into I equal to I into A equals A. Okay? So identity exists in SLN of R. So what about inverse? determinant, let A belongs to SLN of R. This implies determinant of A equals 1. And the determinant of A is 1 means A inverse exists. What is determinant of A inverse? 1 by determinant of A, which is equal to 1. Okay?
Okay, ma'am.
Yeah. That means A inverse also belongs to SLN of R. So we proved all the conditions for a group. What does that mean? SLN of R is also a group. In fact, SLN of R will be a subgroup of GLN of R. Right? Is this clear? Okay, I think let's stop the session today. So anyone is having any doubt in this session, any question, you can ask now. Everything is clear for everyone?
Yes.
Okay. Okay, then we will stop the session today. Again, we will meet the next week. If you have any doubt, you can ask. Otherwise, you can leave the meeting.
Excuse me, ma'am.
Yeah, yes.
Can we have the recorded session of this problem solving?
I think last 2 weeks recorded section already shared with you, right?
Because I was unable to join and I missed the session.
Yeah, I think at least week 1 is uploaded, I think. Otherwise, anyhow, you will get all the recorded sessions.
Thank you.
Yeah, okay.
Okay.
Okay, thank you everyone. So, if no one is having doubts, I am ending the meeting now. Thank you everyone for attending.